Okay, so essentially, I'll start really from long ago. So I said I'll go from classical to then modern approaches, and also see how in application, structural motion and SLAM are really closely connected. This is very long ago. This was essentially the first system that really combined, that went from images all the way to dense 3D models, as you can see here. Here's another example of that, starting from a video sequence. And then going, doing structural motion, computing the trajectory, and then from that go all the way to 3D models as the one you see up here. So this is long before NERF and so on, we could get kind of quite accurate, detailed three-dimensional reconstructions from images. This was about 20 years ago. We were mostly working on images that were very carefully taken, one after the other, or video sequences, because we couldn't really match between images. Once SIFT came about, that actually really changed things. People started doing photo collections, as the few works you see here. You could match images that you didn't have to be a computer vision person and understand what algorithms and matches could do. You could actually work with quite unrestricted images. Here's a few examples. One of my student Chang Wu, who then continued at UW and built Visual SFM, over the years, and this became one of the standard pipelines for structural motion. We continued trying to make this a lot faster, do things like this, scale this up further to really large-scale collections, and that, in a sense, then all converged into ColMap, which today is often used as a reference pipeline to figure out how images, sensor data essentially relates to each other, and then also enables dense multi-view reconstruction also on top of that. One of the key applications, often in systems where you have an environment, you need to map the environment, you need to localize in the environment. Those questions, SLAM, you do all of it together. There's many scenarios where you might do first one and then use the other, and it's a space that you're not, like in an emergency scenario, discover once, and then, and have to map it at the same time and do all of this the best you can in a simultaneous joint problem. There's many scenarios where you can actually afford, you map at some point in time, maybe you'll update the map and so on at later times and so on, but most of the time you're actually just using it in localization mode. Typical pipeline up here is an example of some work did with Thorsten. I saw Thorsten here, and Bernard Seissel was a PhD student working on this, doing localization by voting. Features would vote on where they might have been seen from, and is allowed to actually scale very nicely, and also became, as Bernard moved to Google, became actually the base, the starting algorithm for the street map navigation. Here's an example of something we've been working on more recently, but using a lot of these classical techniques. Essentially, you walk around with a device like the HoloLens. The key value is to be able to access, get questions answered about questions about the environment, know what's in front of you, being able to have, let's say, a digital representation of the environment aligned to the real world, and be able to visualize that. How do you build those maps? Many different ways, but one of them is really just by walking around. So essentially really SLAM. But then when you combine SLAM with then puzzling, you have on-device SLAM, you combine that with cloud, the data from the device gets pushed to the cloud. As multiple people walk around, this data comes, all comes together in the cloud. In the cloud, in a sense, you're really puzzling all of this back together and then optimizing, of course. So that's what you see here. You can have not only people, but also other agents that have cameras and sensors can all come together. And here you see some examples of how of this can all come together. You have also depth data, or you do multi-use stereo and so on. You can also extract different layers. And here's a few examples of the type of representations you can build up. And so you get a kind of SLAM system in the cloud that also has on-device SLAM systems all work together in building these larger representations. Here's an example of then using this at scale in a factory setting to support frontline workers, so people that are in the real world, working with their hands, trying to solve problems, in the real world, and so maybe get assistance from someone remote. So here's an example of how these maps kind of come together at that scale. Here you see all the trajectories. It means we can also support actually people, navigating people through those environments. If we know where different points of interest are, you localize in one location, you can be navigated to the other location. This is a space of about 100 by 100 meters roughly. The map was obtained by just walking around with the device like the HoloLens, or with HoloLenses. And then all of this, being moved to the cloud and optimized, and you get these type of large-scale models just coming out of them. Okay, so let me now switch gears to some modern techniques, some more recent leveraging deep learning, leveraging the fact that we don't have to hand tune a lot of things. We can actually, from data, leverage a lot of data to fit functions that will actually do the right input-output behavior based on just showing a lot of examples and learning from that. Or also bootstrapping from one task to another task. In this case, this was our D2 network, which essentially was leveraging a semantic network to then do both detection and description of features. So instead of having those in two separate stages, like in SIFT, you have difference of Gaussian kind of detection, and then you have a whole descriptor on top of that that looks at gradients and so on. In this case, it's actually the same network that both you find maxima in that network of responses in particular channels in that network, and then you actually use the response in all the different channels as a descriptor. So same network for both purposes. This works very well across wide changes of viewpoints and across, because of the more semantic kind of, also across change of illuminations that you see day-night type of scenarios and so on. The downside is that the localization was less accurate, which is typically is with those more semantically inspired networks. What we then did was look at, could we do better? Because once we match, so there's a big difference typically between tracking and matching in structural motion in these type of problems, or in SLAM. As long as you track, you can really, you have a specific template, and you look back the exact location of that template as it moved in the next frame or so. If you do extraction, you extract independently, and then you match. And so you might actually extract a slightly different point that still, can be matched, but you might not have exactly the same very precise location. So the idea was, once we have extracted in both images, and we know those two are matching, can we refine the location, knowing how the other patch locally looks like? Can we do a refinement step? Okay, and so we bring that in structural motion. It's actually a very easy step to insert in a structural motion pipeline, as you see up here. We actually also later revisited that with slightly different concepts. We also looked at the possibility to learn the features directly for the purpose of relocalization. Okay, so in this case, at some level, we assumed we had already a 3D point reconstruction, but we wanted to learn features and multi-level features that would be helpful for relocalization purposes. And so the goal was actually to put that in a backpropagation framework, and now just train the features that will do best at relocalizing and allow us to do a gradient descent locally at different scales to the proper localization. It kind of works like this here. You start from the closest image, so you assume that you have a way to find the promising nearby images, and then you essentially have these gradient descent steps that will essentially refine and try to align this kind of feature metric representation, align these there's feature response as best as possible to each other. And in a few steps, you essentially get a localization. The nice thing is, by learning this, we not only learn these features, but we actually also learn the confidence of these features. So as we extract features, we essentially determine, is this feature that we just extracted, is it a useful feature? Is it a feature we should actually rely upon? Or is it a feature that maybe we should ignore because we know it's kind of ambiguous, we know it's not very useful for the purpose of localization, because we trained it in, on a localization setting. Okay, so what you can see here is that it actually figured out that cars are not very useful for localization. The algorithm figured it out. We didn't have to tell it anything, or say ignore cars or something like that. It just learned that things that look like cars are pretty useless for localization, because of course those cars tend to move and appear in different places at different times, as you do the localization problem. they turn out to be useless for localization. And so the system just learns to ignore those very nicely. Also here you see at the finer scale, it learned to ignore these very fine repeating structures like bricks, which are also blue and so kind of are low, are weighted low in terms of prominence, is because they can very easily get confused between those features, and so it kind of learned to ignore. So here also we actually use this system to then do auto refinements that in structural motion, very much inspired by also the previous work you just saw. Then in terms of matching, and this is actually work that will be here at the conference. So there's this more work by Philip Lindenberger, who's one of my students, who's here in the audience also, and Paul-Edouard Sarlin, who's also somewhere there. So light glue is essentially, many of you might know about superglue, which is using super points, and on top of that super glue to actually try to really refine and find and have these kind of self-attention and cross-attention mechanisms to determine a good set of promising matches on which you can still do ransack afterwards, but have a much better set of matches between a pair of images. You see that here with light glue, we can actually outperform all of the existing methods. And in particular, a really nice concept here is that we do this multi-stage, multi-layer refinement of these self and cross-attention steps. We can do these multiple layers. We do it up to 9 layers, I think. And you can actually learn to abort early. If it's an easy problem, as the one you see on top here, you can actually do a few steps and then say, okay, I'm good, I converge, I'm good enough. I don't need to do more effort. And then when it turns out to be a really difficult pair, where the images are much further apart, much bigger scale difference or something like this, you need to iterate a few more times to get to a solid set of matches between the two images. That's fine. It just does a bit more work. On average, on a large collection, this can make a huge difference in average speed. Of course, here's a few more examples of light glue at work. And as I said, you'll get all the details by going to the presentation of Philip, to Professor Philip and one area I won't have the time to go into is we've done a lot of work as you do these kind of settings where you do mapping and then other people might use your maps and so on. It's also important, or also you are submitting queries to the cloud, for example, these type of scenarios, you're submitting the equivalent of images to the cloud. Starting to ask the questions, how much information are we actually sharing? And how much information, is there maybe some information we would not like to share? Do we have options to still get localized, for example, if that's what we're trying to do as a task, but at the same time, not share information that we might be concerned about in terms of privacy. So lots of different work here. The key idea was to say, well, for localization, we kind of need some localization constraints. But when we get a point localization, a 2D point or a 3D point, we have already more than one constraint. Typically, essentially, having a 2D, 3D correspondences gives us 2 constraints at a time. The key idea was, okay, what we'd actually do is we'll drop one of those constraints. So we only get 1 constraint per point instead of 2 constraints per point, but that's still enough. If we get more points, it's still enough to localize. But that way we share a representation that's not anymore easily interpretable. It reveals a lot less information. You can do the typical reconstruction attacks don't work. We have these line clouds and 2D and 3D line clouds, depending on what setting you have and what privacy you want to preserve and so on. We build a whole structural motion pipeline and some kind of system in this context. We also apply the same concept in feature space, where also there, instead of having a point vector in a high dimensional feature space, we can actually relax that to an ambiguous linear subspace in the feature space. And what still allows matching, it's a little bit degraded, but allows matching, but reveals a lot less about what, the details of what was actually visible in the image and so on. And so most recently, we have work also here by Linfei Pan, who's the first author on the work on the bottom here, that is also preserving localization and actually can counter some of the attacks that Thorsten here did on some of our earlier work. And and so has some very nice advantages compared to the previous techniques. And again, you'll get all the details out of the presentation. Okay, so now let me switch to mostly instructional motion and SLAM. People have mostly focused on point features. For good reason, they're easy to work with, you get 2 constraints at a time, and so on. But there's also many scenarios where if we're in an environment like this one, if I look around, I see a lot of strong line features, you know, that are very stable, and very few point features that would be stable. So we think that in especially indoor human-made environments, we're kind of really underutilizing the potential of lines. Now, we're not the first ones to think that. So lots of people have tried to use lines. It's always very difficult. There's a number of reasons for that geometrically in terms of conditioning and so on. You get less information. For example, from 2 images, there's strictly no constraints. If you have a random set of lines in one image, a random set of lines in the other image, you make random associations between them. You can all back project them and you get some 3D lines reconstructed. There's just no constraint, right? In 2 views with points, you have the epipolar geometry that constrains how points can be located, you know, with respect to each other. So there is some internal consistency constraints available. This just doesn't exist for lines. Okay, so lines are much harder to use in a sense, but if you use them properly and you do everything right, they're actually super, super useful. So here's some examples showing you also just with a few lines to capture immediately a lot more work here. So I'll very briefly talk about a few different, you know, work in the line space. Actually, I think I'll mostly skip it, but essentially there's very nice work by Rémi Poitras on detecting and describing lines, and then really nice work by Xiaoyi Liu on actually using those lines in a structural motion context and getting very nice reconstruction there. So I'll kind of skip through this here. Also, so detecting lines, extracting lines, describing lines, matching lines. I mentioned light glue before, and super glue here, essentially, glue stick is specifically looking at points and lines in that same context of matching them, both the points and the lines, also in an efficient way. Here, kind of showing you how that's being tracked, how the lines are being matched, essentially matched between the image on the left and the image on the right. Showing you also that many of those are much more stable than typical point features. Then LIMAP is essentially think of ColMap, but for lines. It can both combine points and lines actually, but really focus on the line reconstructions. Here's on some of the tanks and temples data, I think. Seeing that with relatively sparse set of lines, you actually already capture a lot of the structure, and you can do pretty nice reconstruction. That was ETH 3D data. So here are a few more examples and applications for using lines, and a few work in progress to kind of continue extending and bringing more structure in and solve more general problems. I wanted to finish with also highlighting this new benchmark, the Lamarck benchmark, where we're really pushing, we can try to capture a lot of data over different times of day, different seasons. It's both indoor and outdoor data. For now, we have these three large sites, 2 at the university with some indoor and outdoor settings, and then also part of downtown Zurich, kind of with cobblestone streets. We captured both AR headsets and phones, but in AR type of settings. So not single picture at a time, which we think is very artificial localization from a single picture, but more you are actually going through an experience and you want to localize. Capture lots of different data, so multi-camera rig, when you have a device that has more than 1 image, RGB, depth, radio signals, all of these things, and new data. We also collected ground truth data then with high-end scanners, brought all of this together, lots of effort here being done in the group to realize this. Actually, it's a collaboration between Microsoft and ETH at this point, but we're also looking at bringing additional partners on board to build out this data set further. So here you see many of those examples. So all of those dots are essentially different trajectories localized in those environments. By the way, the people that really drove this at this point are Paul Edouard and Fabien and Mihai Dusmanu. Here you see large temporal extents or different times of day. Also, you see here different settings in the environment, construction sites, etc., etc. This shows the accuracy. So we really have most of the data, almost all the data is within a centimeter accurately localized with respect to the ground truth maps. Just showing you a little bit of this ground truth at scale. It's all with depth. So we've aligned it to accurate depth, have the normals, all of this data. And so all of this data is being made available also for, training potentially for different tasks, etc. It kind of showing you the quality of the alignment between the night sessions and the depth and all of those things. So what we really focus on is not the single image scenario, but it's really the scenario where I'm starting experience. I accumulate a stream of data. So I'm kind of moving around and I want to get localized. And so the question that we ask is, how much data do I need to accumulate? How much sensor data do I need to accumulate to be able to have a good localization? So by when do I have enough data to localize accurately? Right? If I just notice this is not the scenario where I'm in front of a landmark, I take a picture of the landmark and I ask what the landmark is, which is a very easy problem. The landmarks are visually very rich, typically are quite unique because they're landmarks, right? So they're quite unique, et cetera, et cetera. Here we're talking, I'm just walking around an environment randomly, looking around and through an experience, a mixed reality experience or so, and I'm just collecting data. And so it might be very ambiguous. I might be looking at a white wall, this type of thing. Okay? But over time, I will accumulate enough evidence to know exactly where I am. That's the scenario we're looking at here. Okay, so here kind of showing how different settings, for example, here including Wi-Fi and radio signals, allow to disambiguate much more quickly, and therefore we need a lot less visual data to solve the problem. But that's kind of how much data, how long a length of sensor data do we need to solve the problem, right? Here, if we threshold it at 10 centimeter, 1 degree accuracy. So remember, ground truth is about 1 centimeter accurate. So we kind of set up the benchmark for visualization at 10 centimeter, as we, believe we can, or ground truth is more than accurate enough to be able to measure that. You have the image setting, and then you have a rig if you have a device like HoloLens, plus radio signals, plus then adding sequential data. These are all the percentages of successful localization within those thresholds that we can achieve. And then, we essentially want to point out that this just single image is a bit of an artificial setting that most people use in other benchmarks. But this benchmark is also not saturated yet. So if you look at how much data would be theoretically localizable, essentially almost all our data should be localizable, and we're still far from actually localizing all of it, even when we use all of the data available. So this is roughly the size of data. So 500 gig of data, 45 hours of captures in many short, few minutes sequences with these captured with these different devices. We're also working on extending that. Okay, so if somebody wants to see the QR code, there you go. But just look for Lamar otherwise, and you'll find it also. Okay. So we're also working on extending this to robot data, like in more emergency scenarios like here. The additional challenge is that instead of being sensors at eye height, now you have sensors at a very different location. So the cross-localization can be quite challenging. So this is examples of how recent captures this kind of emergency.
Can you maybe look around a bit?
Okay, and then really last slide here is also in all of this, not only geometry, but beyond that, also bringing in semantics is something that, in my group, we've been working on for the last 10 years at least. Here's some of the latest work, which was a collaboration with Google. It was actually a Google internship with Tom Funkhauser, and the student is Song Yu Peng, who's actually graduating soon. Doing some really nice work here on essentially using CLIP that connects word embeddings to image embeddings to extend that to connect it to 3D point cloud embeddings. And then when you have a textured 3D model, so from textured 3D models, you can train all of this. And then when you're given a textured 3D model, you can compute embeddings both from the images and from the 3D. Given those embeddings, now you can pre-compute this on the whole 3D model, as you see here. And then when you're given a textual question, a textual description or a question, You can enter that, you generate an embedding, you correlate it with the whole scene, and you see where the strongest response is. You can normalize that as you see here, and then the strongest response is probably the most relevant answer, you know, of a place in the world. That's the part of the environment that's most relevant to address your query, right? And then to finish, for all of you interested in 3D, which as many of you are, I want to kind of remind you, it's too late to submit papers, but definitely not too late to come and attend. And I hope many of you did submit papers. We certainly had the most submissions until now. Davos, March, still, you know, still a month to go in the ski season at that time. There's also good opportunities for students to come for actually very, very cheap. We have a deal with the youth hostel for $60 or so per night, including dinner. So actually very good options for you to come. So if you're interested in this, check it out. And I hope to see you there. And I'll stop there.
Hi, for I have a question about the Minecraft. So like usually in robotics, a lot of applications use fisheye cameras because like would it actually affect the line detection or like constructing the line map?
So certainly at the low level line detection, yes. I mean, you'd really have to you'd have to be careful of how you kind of run. You'd have to adapt your. I mean, either you'd have to retrain a network that's specifically targeted to those cameras, but you can also do it properly by just rewarping. But you have to be very careful in how you do that in terms of sampling. In general, the fisheye cameras are mostly tend to be kind of equiangular. In that sense, it's not too bad. So you kind of a very wide field of view with a perspective camera has a lot of distortions in the angles. Here, you actually see in every direction you have the same amount of pixels visible at anywhere in the image. If you have a good quality fisheye camera, you have the right data to extract those lines and extract them over, vanishing points. You can, like lines in a hallway, you can now see them from beginning to end in a fisheye camera. So on the one hand, you're much better. The data intrinsically is much better, but at the low level of detection, you would have to do quite some work to make sure you extract, like in the best possible way from the raw image data, because of course it's not straight lines there. All of that can easily be treated with geometry, but you'd have some, dedicated work to adjust the first steps of your networks or do some mapping to do that. But otherwise, those would be great cameras for that. Yeah.